Okay, good afternoon, everyone. It's my great pleasure and honor to have this opportunity to present our research. And today, we are going to talk about the use of nanotechnology to improve food safety and sustainability. And specifically, we'll talk about how we develop nanosensors and nano coatings to improve food safety and sustainability. So as everybody know, there are many challenges in the current agri-food systems, and with the rapid world population worldwide, they pose a great challenge for the needed increase in food productions. FAO also highlighted that 1/3 of the food is wasted in the food supply chain, mainly due to the contamination, poor quality, and the spoilage of the food, and also food packaging operations. So those food waste will impact our environments, limits available land and water for food production, and also cause climate change. So those negative climate environments can also add in more stress for sustainable food productions. So ensuring a safe and sustainable agri-food systems is important to increase food availability, reduce adverse environmental impact, and improve human health. So for the food contamination, the source of the food contamination can occur anywhere in the food supply chain, from farm to table, from the raw materials in the field or the farm to the food processing facilities and the packaging before it reaches to our tables. So it's very important to develop a rapid, sensitive, and field-deployed tools to improve the food safeties. So in addition to measuring the food contaminants, it's also important to develop sustainable materials to actively protect our food and agricultural products, and to reduce food waste as well as to increase food availabilities. So nanotechnology-enabled platforms is promising to address challenges in our agri-food systems, and specifically in our lab, we use complementary directions in the nanotechnology, specifically nanosensors and nano coatings to tackle challenge in the agri-food systems. So we develop nano-enabled sensing tools for the detection of the contaminants. And we also develop nano-enabled coatings and materials to reduce the risk and to extend the food qualities. So we integrate some multidisciplinary approaches in food science, analytical chemistry, nanotechnology, and material science to create the practical solutions as well as the integrated nano-enabled platforms to improve our food safety as well as our sustainability. So in the food sensing aspects, enhanced of the sensing of the food contamination should be more frequent and larger in scale and implemented from farm to fork. But currently, there are several challenges in the fields. For example, high cost of the examination, time-consuming operations required of trained personnel's invasive detections. So we classify the nanosensors used in food, agriculture, and drinking water in 3 classes, especially for the class 2 as well as class 3, rapid analysis in the fields and real-time monitoring devices in the farm and package. It's very important to develop rapid, accurate, and on-site testing methods for more proactive and convenient food analysis. So among all the nanosensors we develop, one central nanosensor we use is a surface-enhanced Raman spectroscopy, often called SIRS. So SIRS is a vibrational technology that combines Raman spectroscopy and nanotechnology. When the laser interacts with analyte, it can produce Raman scattering. And however, the Raman signals is very low, but when the analyte interacts with the metallic nanostructure, such as gold or silver nanoparticles, the SIRS signals can be dramatically enhanced to produce a surface-enhanced Raman scattering, also called SIRS signals. So in the SIRS concept, there is a mechanism called hotspots, which means where the 2 nanoparticles are very close, and the gap at the 2 nanometers, and when the target molecules in these gaps, their signals can be dramatically enhanced. So this allows us to design ultra-sensitive SIRS detection for trace analysis of our target molecules. So SIRS has shown several advantages. It can provide the fingerprint information of the target molecules, and we can achieve in situ or non-destructive data acquisition. It can achieve ultra-high sensitivities, and based on the characteristics of the peaks, we are able to establish a linear curve for quantification. So next, I'd like to show several case studies of the nanosensors we have developed to improve the safety. The first one is detect of micro and nanoplastics. So guess some of you may already see the news last year. Ziploc, which is the famous brand, is facing action lawsuits over its microsafe labeling. So researchers have found that there are hundreds or millions levels of the microplastics or nanoplastics can release during the microwave processings. So those micro and nanoparticles, we call it the micro and the nanoplastics. For the nanoplastics, it has the smaller size, less than 1 microns. Because it's a smaller size, it has more challenge for the detection, as well as potentially causing more health risks. So in our lab, we developed a portable device for the detection of micro nanoplastics. And we use a novel luminescent metal phenolic networks, we also call it LMPN, to labeling micro and nanoplastics. Metal phenolic networks is the coordination between the metal ions as well as the phenolic compounds. And those metal phenolic networks can further interact with the luminescent dyes, for example, rhodamine B, to form to self-assemble into coating layers onto the plastic surface. It will show the ultra-thin coatings, and the labeling process is very quick. And we can also change the dyes to tailor the luminescence of the properties. And it also shows very stable fluorescence signals that allows us for the detection, do the imaging analysis. So over here, we develop a portable device connected with our cell phone. And this portable device is fluorescence-based. And we can image the coated plastics into the fluorescence image, and we correlate the fluorescence image, the pixel area, with the quantity of micro and nanoplastics. So over here, we add the machine learning algorithms in our cell phone, and this allows us to directly read out the numbers of the micro nanoplastics as well as the positive or negative signals in our samples. So this method is highly feasible and cost-effective. It only takes 1 microliter samples. It doesn't need trained personnel, and it will also achieve a low cost. And for each of the tests, it only takes 1.5 cents. So using this method, we evaluate the micro nanoplastics from the release from the commercial cups, different plastic cups. We add in boiling water into the cups and let it cool down naturally. And after 30 minutes, we measured 100 million levels of the micro and nanoplastics in our hot water. So can you imagine how much micro and nanoplastics you can potentially exposure if you just drink hot water or hot coffees? So this is a huge issues right now, and the researchers are developing different technologies to reduce these risks. And same as our lab, we are also working on how to remove the micro nanoplastics in our human bodies. So as I talk about the nanoplastics that has a smaller size and a potential more challenge for the analysis and health risks. And after that, we also develop a SIRS-based method coupled with machine learning for not only detection, but also classification of different types of the nanoplastics. So we're first using MPN to label the nanoplastics. This can help extract the nanoplastics into the water mediums. And after that, we generate the SIRS spectrum with different machine learning algorithms. We can do the classification and quantification. We achieve a very good classification and quantification accuracy, and we are also able to identify different types of the nanoplastics in the mixtures, even in the real water, tap water, and the lake water systems. So in addition to the micro and nanoplastics, we are also interested in the PFAS. I guess many of you have heard about this PFAS, right? So this is considered as the forever chemicals, and it's a group of the chemicals. And for example, PFAS is the name. It may contain PFOA, PFOS. So this is the fluorinated man-made chemicals, but it's highly resistant to all the environments, and it can bioaccumulative in our human bodies. And the researchers found our human exposure to PFAS is primarily due to drinking water and food with those PFAS contaminated. So this urged us to develop a simple and effective way to detect the PFAS in our food and water systems. And over here, we develop a search method coupled with coordination-driven assemble. We use zirconia ions as the bridge between citric acid-coated gold nanoparticles and PFAS. So in this study, we use citric-coated gold nanoparticles as the search substrates. And then when we're adding zirconia ions, and they will cause the nanoparticles aggregation due to electronic stickers. And when we add in PFAS, for example, one type of the PFAS, PFOA, it will reduce the aggregation and causing a lot of hotspots in the search, so which allows us to ultra-sensitive detections. And using this simple method, we detect different types of the PFAS, including PFOA, PFOS, and PFBS. And our limit of detection is as low as 1 ppb levels. And using this coating coordination driving, we can also simply remove the PFAS into our water systems, and we got the removal rate higher than 99%. So although nanosensors, they can detect the contaminants, identify the issues, but detection alone is not enough. So we are also interested in designing proactive nano-enabled materials to actively reduce the risk and improve sustainability. And here I show several aspects we are working on right now. For example, preserve our fresh produce, remove pesticide on produce, develop smart and sustainable packaging, and also develop seed and fertilizer coatings. So one type of the coating we use is relied on metal phenolic networks. So as I showed before, it's the coordination between different polyphenols as well as the micronutrients. And they can form a thin, uniform, and highly tunable films on as the coatings. So these coatings has several features and advantage. It has the very simple formation conditions, and we can also tunable the properties by changing the types of the metals and polyphenols. We are able to design the films or the coatings with different mechanical, optical, and barrier properties. And because the ingredients we use, they can show antioxidant, antimicrobial properties, also UV blocking. And more importantly, all these ingredients, they are food grade, so which means they can provide additional nutritional levels to be applied on fresh produce. So for example, for the metal ions, we select the micronutrient ions. So this, as the recent study shows that more than half of the Canadian male and female adults, they can have the micronutrients deficiency, for example, calcium and zinc. So using this method, we are able to address the micronutrient deficiency by applying coatings onto our fresh produce. So when we talk about the fresh produce preservations, it's actually a very comprehensive analysis. So we need to evaluate the produce quality factors, and we can also apply in different ways for the protections. So here I show some of the quality factors that we need to do the comprehensive analysis to evaluate the coating performance. So this includes the physical and chemical performance, physical mechanical performance, chemical performance, microbiological performance, as well as the sensor and consumer acceptance. So here is one example. We develop EGCG, which is a common polyphenol extracted from the green tea, coupled with the iron or zinc oxide. And these simple coatings can extend the shelf life of a fresh produce, and it can reduce the weight loss, retain more firmness, and delay the spoilage. And we further develop MPN coupled with the plant-based biopolymers agar to make MPN agar microparticle coatings. And we compare the coating performance with the fridge conditions. So in the room temperature as well as in the fridge temperature. And very exciting is when we compare the coating with the fridge without coating. We found that our coating performance is actually much better. So this is super impactful because this can reduce the cold chain burden. So this is very important for the transportations when we ship or transport the fresh produce internationally. So this can help us to reduce the cold chain storage as well as for further evaluations. So in addition to the preservation, we are also interested in the decontaminations. So for example, we developed a novel post-harvest process to improve the food safety as well as to extend the shelf lives. So the traditional post-harvest treatment, they have several challenges. They use the wax coatings, so those wax may contain health risks because some of the wax are coming from the petroleum-based source, so this will contain micro and nanoplastics. And also, pesticides is a safety concern, but currently there is a limited effectiveness to remove the pesticide contaminations. So more importantly, there is no single method in the post-harvest processing that can achieve both functions at the same time. So our goal is to develop a dual-function post-harvest process that can not only remove the pesticide residues, but also extend the shelf lives by the coating performance. So here we developed the iron tannic acid capped starch nanoparticles as the new coating and washing solutions. And we can achieve pesticide removal for different pesticides for pre-harvest and harvest more than 90%. And for the coating performance, we can extend the shelf life for both the whole fruit as well as the fresh cut slices. So although we have developed so many lab innovations, the most important is to how to transform the lab innovations to real-world deployment to have the real-world applications. So nano-enabled technologies must be designed with the scalability, safety, cost, and regulatory pathways. And over here, I show several key factors for translation and commercial of the lab innovations to the real-world products, including we need to consider the cost of the materials, the food safety and the toxicity assessment, if the coating is edible or just sustainable, if it can be removed from the coating or the firmly attached on the coatings. And we also need to consider life cycle assessment to reduce the environmental burdens, and also consumer acceptance, processing facility compatibilities, and the regulatory approvals.
Perhaps if you could wrap it up in the next 30 seconds, that would be great. Yeah, thanks.
Last slide. Okay, moving forward. The future studies in the nano-enabled agri-food systems should be designed towards more intelligent and sustainable approaches. So those are listed some of the future opportunities that in the fields and we are also working on. For example, developing sensing and coding in the systems, use AI technologies, and partnership with the different regulatory agencies. So last but not least, I'd like to acknowledge my team member, my collaborators, my funding support, as well as BPI for the opportunities. Thank you very much.